So it's trying to draw a circle. In the xy plane, it's trying to draw circles, but then the z component is making it go up, so it's drawing this spring going up. And what I'm asking is the arc length of this spring from a certain point on the spring to a separate point on the spring. Notice in this problem, I have not given you t, have I? I have not told you what t is, like what the restrictions on t are. I'm not saying between 0 and 2 pi or anything like that. I'm just saying from one point to another. So this spring goes like this, whatever. And I'm asking if you are at this point, I'm just going to pick it right here. If you're going from 1, 0, 0, and then you draw it and you wind up somewhere else, negative 1, 0 pi, right? If you were to look at this right here, what's that arc length? All right, so let's start with what we know we need, which is the derivative, right? Derivative is what? Negative sine t, cosine t, and 1. Now, magnitude of this derivative. Sine squared t plus cosine squared t plus 1, right? So that's just going to be 2 under there, right? Root 2. It's not always going to be a nice number like that. There you go, square root of 2. Now I'm supposed to integrate this from a to b, right? Root 2 dt. How am I going to figure out what a and b are? What do y'all think? Somehow from these points, but how? Those points live on our curve, right? So there's a vector pointing to it, right? That's not going to tell you the t, though. See, isn't t the clock running in the background? Don't we want to know what t generates this point and what t generates that point? Don't we want to know that? So ask yourself this question right here. What t do I plug in to get 1, 0, 0? 0, how? All you have to do is look back at the original vector function, right? And try and just mentally have this little exercise. What t would make this 1, this 0, and this 0 all simultaneously? And it's pretty obvious because this is t, right? So I have to make that 0, so t has to be 0. Let's just check. Sine of 0 is 0, cosine of 0 is 1. So t equals 0 is going to give me that, right? Now what about this one? Pi. Right? To do this, t has to be pi. And again, that's obvious because the last component has to be pi, right? Because it says it. Sine of pi is 0. Cosine of pi is negative 1.
What if in the line function we weren't given something as nice as t to kind of clue us off?
Great question. What if this t was something else that was not as obvious? Well, then you're going to have to figure it out.
Could we create a line function that intersects that point and then kind of plug and chug for a t that satisfies both?
What you could possibly do that. What I would do is just write down what you're trying to get. Cosine t is 1, sine t is 0, and then whatever your third one would be. Those are the first two, right? I'm trying to match up cosine t with negative 1, sine t with 0. So I would look at this and I'd say, okay, what are the solutions to this? When is cosine negative 1? All multiples of pi, all 2. T has to be 2 pi, pi n. Let me do it this way. Pi plus 2 pi n. You have to either be at pi or all the way back around. 3 pi or 5 pi, or this is there are an infinite number of solutions to this problem, aren't there? Yeah. Then you'd have to say, when does this happen? When is sine 0?
It's a pi over 2.
This actually happens at 0 or pi or 2 pi or 3 pi or 4 pi. So this would give you all multiples of pi. And then whatever your third equation is, you'd have to figure out what that is, whatever it is. And then you'd have to figure out what t gets you all of these simultaneously. That would be harder, right? There will be a problem like that. It won't be that hard. You'll have to just squint your eyes a little bit. It's not going to be super difficult to solve the equations. You'll just have to kind of play with some numbers in your head, and you'll hit it. It'll work out. Yeah, it'll come to you. But that's a very good question, because I wasn't going to say anything about that, and I was just going to see how y'all did with that when it's not so obvious.
Well, yeah, I'm just curious, because like, let's say on take-home exam, or obviously you already stated you won't have to, but real world.
Well, it's going to happen on the take-home exam. I can already tell you that.
Not as complicated as I was thinking. Like in the real world, the first component could be like e to the t, cosine, whatever the hell, and then same thing with the y and z component, and then satisfying all three. It's not as simple as just staring at it. So I wanted kind of like an idea of how we would go about that.
Yeah. You're solving three equations simultaneously, all for the same variable. So it's just, that's what it is. Three equations, need to satisfy them, find a solution that makes sure that all of them are true at the same time. All right, so the arc length of the last one, everything has been working out really nice, hasn't it? Like when we've taken the derivative and taken the magnitude, we've been getting nice things. I think this is an example where we're going to get something a little bit different. Why don't I give you about 5 minutes to just see if you can get through the derivative and its magnitude. See if y'all can get that part. Maybe I'll give you more than 5. Maybe I'll give you 5.5. 6 minutes. Okay, I think that's probably sufficient time. Here's the derivative. And then you square each component. So you just got to be careful here. When you square the 1/2 or raise it to the second power, you get just t. Squaring these, the number squares, the trig function squares, the argument doesn't square, right? So that stays 2t. And then you can simplify those last two terms and just turn it into a 4. So you get this, and then you integrate from 0 to 1. That was given. So what is the antiderivative? You would use u sub on that? Okay. So what is the antiderivative of this going to be?
2 over 27.
2 over 27? Sure. 9t plus 4 raised to what? 3/2. And this 0 to 1. Are there any questions on that? Let's plug in 1. What would you get if you plug in 1 here?
2 over 27.
You get,
So 13. 3 over 2.
so you get 2 over 27, 13 to the 3/2, minus, then plug in 0, 2 over 27 times 4 to the 3/2. And whatever that is, right? That's going to be your arc length. This might be worth getting a decimal. I'm not going to do it now, but this might be worth getting a decimal so that you have some sense of how long that is. No questions? Yes?
Maybe I blanked out or something. We're given our t,
Uh-huh.
so we derived it to get our prime t,
Mm-hmm.
and then took the derivative
Mm-hmm.
to get back to our t. Or we
Took its magnitude.
of the derivative,
Uh-huh.
and then derived it,
We didn't derive it again.
integrated it to get our prime.
But we integrated the magnitude. Now, I didn't explain this, like why this formula works very well. I can try a little bit, okay? Like why is this giving us the arc length? So imagine you have a vector function, a curve that does this, and we'll just look at the two-dimensional. And you know what, I'm going to make it a little more complicated because we could have done this in Cal 2. That is the curve that's drawn by r of t. Now in Cal 2, you could not find the arc length of this because it's not a function, right? This curve would have failed the vertical line test, so you couldn't do arc length in Cal 2. Here, it doesn't, it's a vector function. We don't have vertical line tests for vector functions. You don't need it. So this is still a function. Now, what we're doing is we're integrating, we're adding up, right? This is what the integral means. We're going to do this summation of a bunch of stuff. What we're adding up are the lengths of the derivative vectors. So at each point out here, we have r prime of t, right? Which is a vector. Yes? And we are taking its magnitude, which is that length, right? And we're adding them up. Now that seems wrong, doesn't it? Because we're supposed to be adding up these little tiny little infinitesimal lengths. And how is doing the whole vector giving us the length of this curve? Do y'all see how that doesn't make sense? Well, that's where this comes in, the dt. The dt is an infinitesimal, so you're scaling it down. So it would be better if we actually drew like a little segment here. And you get like a little segment. Here's the actual arc. We're approximating it with this line. And so what we're doing is we're taking this direction, this vector, which is r prime, and we're scaling it to get this length. Now, we'd have to go through the algebra to really like make you believe it, but visually that's what's happening. This gives you the direction of the vector, you get its length, and then you scale it dt, scale it by dt to bring it down. Eh? Y'all buy that? I mean, if not, we have to sit through and do the algebra for it to show it. which I'm happy to do. Just come by my office and we can sit down and go through it. All right, let's move on. All right, with vector functions, we have this idea of curvature. All right, curvature. This is something that we don't have anything like this in our normal functions, like f of x equals cosine x. This is only something we can really talk about in terms of vector functions, and that's curvature. So the curvature of a vector function is a number. It's a numerical value, which represents how quickly the curve changes direction at a given point. The curvature can be found by computing one of these two formulas. So there are two formulas that you can use to get curvature. There they are. The first one, we use this k for curvature. The first formula is you take the magnitude of the derivative of capital T. Do you all remember what capital T was? It was the unit tangent vector. So capital T, I'll write it up here in case you've forgotten. Capital T of T is the derivative of r divided by its own length. Capital T is the derivative of the vector function divided by its own length. That is not what we're using in this formula. We're actually using the derivative of this. That's what we use in the formula. Okay, and then we divide that by what? The magnitude of the derivative. Okay, that is going to tell us at some point how fast the curve is kind of turning. The other formula is this one. You take the first derivative of the position function, you cross it with the second derivative, you take the magnitude of that vector and you divide it by the derivative of the vector function, take its magnitude and cube it. Your choice. They both look nasty, don't they? So the natural question I get from students is, which one should I use? Should I use the number 1 or number 2? And I'm going to do an example now where you're going to see, oops, hold on a second. Did I unmute? You get to choose the formula. over 1.
Then you get negative cosine of t, and then just sine. Take the magnitude of that. So just 1 over 1. Negative sine. This seems easier that way.
How many of you did the first formula again? Okay. How many of you are done using the first formula? Cool. And you got one? Okay. Try the second one then. And what I'm telling you is for r of t, just add the 0 to the last component.
Seems like a lot more work.
I agree.
The second formula, I just got them doing it. It gives you 1, but it's just.
It does give you one. It's just a lot more work. Yeah.
And it could mess you up because at the end, like the cross vector is 0, comma 0, comma sine squared t minus cosine squared t.
So you have to factor negative out and then do 1 and then take the absolute value. Okay. Anybody working on the first formula that has not got 1 yet that needs help? On the first, using the first one to get 1? Yeah? Where are you at on it? Okay, so all you're doing here is you're dividing this vector by 1, which means just each component divided by 1, which would just leave you with the same thing that's there. Okay? But that's actually, that's not t prime though. That's just t. Okay? So t of t is just put equals here, and then just put this vector, not over 1. Okay, now the formula says you need the derivative of that and its magnitude. So you got to take the derivative of this again and then find its length.
Where's that 1? QE? It's 1. I guess the 2-dimensional would be easier. You're not giving sine and cosine.
Okay, I'm going to move on because I only have 13 minutes. But you should be able to get that the curvature was 1 using either way, using either method, and then you would kind of make your own judgment there as to which one you liked better. Seems like people liked the first one. This example is just a visual of a different type of vector function that does not have a constant curvature. The circle has a constant curvature. This one doesn't. And I have the computer can show you, it's going to calculate the curvature for you. And you can see the curvature in the beginning is kind of a large number, but as we move along this path, the curvature gets smaller. Does that make sense? It's a tighter spiral in the beginning, so you're curving faster. It's a larger curvature, and then it gets smaller as you go on.
We can have that on the midterm.
What's that? Look at this one right here. I think I'm going to work this one with you. Let me make sure this is the one I wanted to work. See if there's one after this. Yeah, this is the one. All right. Okay, let's try the first formula. We're going to work it together. So what do I need to do the first formula? It's the derivative of t, right? Its magnitude over the magnitude of r prime t, right? That's the formula? Okay, so what is, let's figure out what t is. T of t is r prime over its own length. What is R prime? 1, 1, 2t. Ah, this looks unassuming at this point, doesn't it? This doesn't look too bad. Okay, I'm going to divide that by its own length. What's its length? Square root of 1 plus 1 plus that squared, so 4t squared. So 2 plus 4t squared. So this vector becomes 1 over square root of 2 plus 4t squared, comma, 1 over square root of 2 plus 4t squared, comma, 2t over square root of 2 plus 4t squared. Are y'all okay with this? You're taking this vector and dividing each component by the magnitude. So you take 1 over this, 2t over this. You got this, right? This is just what? Capital T, right? What do you need now? To take its derivative. Yes? All right. What is the derivative of that? The derivative of that is doable. But do you see that we're starting to get into some territory where this doesn't look fun? Because even after I find this derivative, what am I going to have to do with that? Take the magnitude. So I'm going to take each component, square it, take the square root, right? And then divide that. Oh my goodness, this looks horrible, doesn't it? So maybe the second formula is better. Maybe the second formula is better. Let's see. So I'm kind of waving my hands at this. I'm like, I don't know. Okay, so let's try the other formula. The other formula is the magnitude of the what? First derivative crossed with the second derivative, but then over the magnitude of the first derivative cubed. All right, now we've already taken the first derivative, haven't we? I'm going to erase this. Let me erase this. That is your first derivative right there, right? What's your second derivative?
0, 0, 2.
0, 0, 2. I need to cross these two vectors. So I cover up this component, right, and I do my little thing here. What do I get? What's R prime T crossed R double prime T? So my first component is what? 2. Second component? Negative 2. Third component? 0. Ooh, I like that. What's its magnitude? It's this squared plus this squared, right? And then root. So root 8? Yeah? Root 8? Over? Now, what's R prime is this, right? R prime is this. Take its magnitude. What's its magnitude? This squared plus this squared plus this squared, which would have been square root of 2 plus 4t squared. But then all of that, what? Cubed. That's my answer. That's the curvature. That means it is not constant. Because look, the curvature depends on what? T. You need to give me the t for me to give you the curvature. We did not get just a constant here. Like on the previous problem, we got 1. So do you see now what I mean by sometimes you want to use the first one, sometimes you want to use the second one? If you sit there and go, I'm only going to use the first one, man, because that's the one I like, then this problem is going to be very difficult to do with the first one. It can be done, but the algebra in that's really tough. So can you explain to me, just by looking at this picture, or this result, what happens to the curvature of this curve, this function, as time goes by? As time gets larger, what happens to the curvature? It gets smaller, right? As t gets big, this number gets big, root 8's a constant, the fraction should then get smaller. Okay?
So are we going to start getting into the curvature of a function, or a curvature of a vector function as a function?
And look at that as a function?
Yeah. Because like it changes in relation to time.
Yeah, but this would be more like your standard function from regular old algebra and calculus. This is a function of one variable. It takes in a number, it spits out a number. So this is not a vector valued function. You could graph it and analyze it. You could take a look at the graph and see what's going on. But all that would be telling you is what's happening to that curve, what's the rate of turn, basically, on that curve as time goes by. And that's it. Wow, look at that. We got through both these sections today. Outstanding. Let me pass around the sign-in sheet. If I have it, I may not have it. I didn't bring it because I handed out the tests. Anybody not get their exam? Do you all have any questions? Yes.
What if in the curvature we were at some point divided by 0? I know in this one we can't.
Mm-hmm.
But if the curvature is undetermined at some point, what happens to the vector function?
The question being asked is, what if you have a curvature where at some point it's undefined? Like what's going on with the graph? And I think I can actually show you an example of that with something we looked at before. Let me see, maybe in this section, yeah. Do you remember when we were talking about smooth? Let's see if we have it in here. Where's smooth? It's coming. Smooth. So I gave you this example right here. You're free to go. I won't keep you if you don't want, you're not going to hurt my feelings if you want to go, but I'll answer your question. So let's look at this one right here. I'll show you the graph just so you can recall what it looked like. It was this one. Remember that? So when you think about curvature, you have some curvature happening here. It looks like it's a small curvature, and then it looks like it's getting fat, like a larger curvature. Then we get to here, like something has to happen, right? I wonder how difficult it's going to be to compute this curvature. I'm going to try the second one. But man, it's really not looking good. The first derivative of this one is some chain rule 2, -2 sine t cosine t. That's a little chain rule. And then 4t cubed. And I'm going to do a 3-component just so I have it, all right? I'm going to clean this up just a little bit. This is the same as negative sine 2t. That's just using a pre-cal identity. Okay, I just don't like that. So I'm going to put it here like this. And then now let me take the derivative again just to see how bad it is. And when I take derivative of that, it's actually not that bad, right? It's minus 2 cosine 2t, and then 12t squared, and then 0 again, right? And let me try crossing these real quick. Okay, let me cross them. So I cover this up. What do I get for my first component? 0. That would always happen. If you extend this to 3 dimensions, that would always happen because these will always be 0. So r prime crossed with r double prime is going to be 0, and then cover this one up, 0 again. And then finally cover this one up. This one's going to be the ugly one. So it's going to be negative 12t squared sine 2t, and then minus, right? So plus 4t cubed, no, 8t cubed cosine 2t. Y'all agree? Okay. Good. Now, the formula says I'm supposed to take the magnitude of that. Let me take its magnitude, and we're going to get whatever we would get up top, right? The magnitude. I'm not even going to write it down, the magnitude of that. But the more important thing is the denominator. Look at this denominator here. The magnitude of the derivative, first derivative cubed. So what's the magnitude of this? Sine squared 2t plus 16t to the sixth, right? And then what, square root? And I can see a problem at 0. Do you see a problem at 0? So at 0, you're going to get 0 here and 0 here, so it'll be undefined. So your curvature has an issue there. It's undefined. So your question was reverse of that. Your question was, what if there's a problem with the curvature, right? What does that say about the graph? I answered your question by giving you a graph where it had a problem, right there. That was at t equals 0, and showing you that the curvature was undefined there, right? That doesn't directly answer your question. But what we can be sure of is that if the curvature is undefined, we must have something like a cusp or a sharp corner where our curvature is changing instantaneously from one thing to another, or possibly even just like asymptotic or something.
Do we have to note that the equation cannot be equal at that point at 0?
Do you have to what?
Do we have to, can we notate that that point at 0 is undefined?
Well, the thing is, the curve itself is defined at 0, right? Like the curve, you can plug 0 in, and there's no problems with this curve if you plug in 0. But you can't talk about the curvature at 0 because it's undefined.
So would we have to state that though?
What?
Would we have to state that? Is that the curvature at 0 is undefined?
If you're asked to find the curvature of something, then I don't need you to state its domain. I just need to know what the function is. Yeah. Does that address your question? Okay. If your curvature is undefined, you've got something happening there. I think the bigger question would be, does it have to look like this? Is there something else it could look like that you would still have an undefined curvature? Here's one that comes to mind. I mean, this, you should also have a problem. You should also have a problem there, but I'm trying to come up with something where... Like I'm trying to think of one that does something like this, where I start t equals 0 here, and I start drawing in this direction. And what I try and do is spiral myself in so that my curvature keeps tightening, and it becomes like an infinite curvature. That seems like that would cause a problem, but then I don't know if I could actually draw this function with that point in the middle defined. See, here the point 0 is defined. At t equals 0, we're defined. I think this would cause problems with curvature, but I don't think I could define it like in the middle. So then we couldn't even talk about curvature in the middle because it's not even defined there. So I have to think about this some more and see if I can come up with an example that you have undefined curvature in something other than that picture.
So, like how when we dealt with smooth or not, we basically rearranged the function and took it a different way. We were able to define it or kind of get an idea of it differently. Because I remember
If
you
it
had
was smooth,
you had your thing set up a certain way, and then when we solved it in class, it was